Atmospheric moisture. First of all, let's look at the visuals. There we go, atmospheric moisture. Visuals, clouds, readily visible. More atmospheric moisture, steam, again readily visible. And indeed, atmospheric moisture coming out on frozen glass. However, there's atmospheric moisture here. Where is it? We have to make it visible to actually see it. How do we do this? By measurement. That is, by producing certain data. So let's first look at relative humidity and vapor pressure. Temperature and relative humidity. At 10 degrees, the air can retain a maximum of 7.5 grams of water vapor per kilogram of dry air. Double the temperature and we roughly double this. So the warmer the air, the more water vapor that can be resident. However, it is important to know how saturated the air is with water vapor, and this is what we call the relative humidity. It's a measure of saturation. Broadly, we can say the amount of water vapor in the air at any given temperature, expressed as a percentage of the maximum amount of water vapor that can be resident at the same temperature, is known as the relative humidity. Therefore, note that relative humidity is a proportion. It is not what one could call an amount. So what are the effects of cooling air on relative humidity? Well, let's imagine the air as a bucket, okay? The warmer the air, the bigger the bucket. Conversely, the colder the air, the smaller the bucket. And so we start off in our hypothetical case here, 20 degrees, biggest bucket, 60% relative humidity. That bucket is containing 60% as a proportion of its volume. What we're going to do now is cool the air, and we're going to cool the air down to 15 degrees. The bucket gets smaller, but we're going to pour that amount of material in the left into this bucket. Same amount of material, but this time the relative humidity has increased to 83%. Why? It's simply a proportion of the volume of that bucket. We're going to cool the air down again. We're cooling it down to 12 degrees. Bucket gets smaller. We're going to pour the same amount of material into the bucket. Our bucket is now full. We're going to cool it down again, of course, to 10 degrees. So what will happen if we pour that amount of water on the left into this much smaller bucket? We're going to get overflow, and basically at that temperature the air can no longer retain the water vapor in it, and it comes out. That is where we get condensation. And indeed, a decrease in heat increases the relative humidity, not the amount of water but the proportion. Similarly, an increase in heat decreases the relative humidity. If we look at surface condensation, this is just simply a principle. The figures aren't actually spot on by any stretch. Let's start off by looking at a cold wall on the right. We have a relative humidity scale there and an air temperature scale. Now here we are looking at what one could call the boundary layer of air. This is the air that is literally in contact with the surface. So we start off in our hypothetical case with air somewhere in the order of 17 degrees and a relative humidity of 76, 77. However, as that air really does come into very, very, very close contact with the wall, it's being cooled, our bucket is getting smaller, and at say 15.5 degrees we have the relative humidity increased to about 88%. And as the air gets cooler and cooler, following the red line down, we get to a point about 14 and a bit degrees where the air can no longer retain the water in it. It's reached 100% relative humidity. This is known as the dew point temperature. And at this temperature, the air is fully saturated. Any more cooling and the water must come out of the air can no longer retain it, and we get condensation form. And it is important to understand that the dew point temperature is where 100% relative humidity occurs. So you're sitting in your office and somebody comes along and says, look, I've got these figures, 60% relative humidity in the room on the left and 70% on the right. Which is the dampest room? The answer is you don't know. Why? It may be purely a temperature effect. Relative humidity is affected by temperature. And again, another hypothetical, or rather just telling us the principle, changes in relative humidity in a property, say in the winter. And there's our property, insulation, timber suspended floor, and we measure a temperature of 20 degrees at 44% RH. It has a vapor pressure. We'll mention this later, give more details, but vapor pressure actually reflects the actual amount of water retained in the atmosphere. So the air moves up and down and round and round, and some of it will get beneath the floor, assuming no ventilation. It's cooled to 13 degrees, so what will happen? Smaller bucket, the proportion increases, so we now finish up with 69% relative humidity. Vapor pressure the same amount of water vapor in the air. And similarly, in the roof, we finish up, it's cooler again, and we get 74% relative humidity, same amount of water in the air. Looking at the external atmospheric conditions, the relative humidity, this is taken from British Standard 5250, 2011 and 2016. Just looking at relative humidity alone, notice in the colder months of the year, the relative humidity that one might expect on average is over 80%. The relative humidity is over 80%. And this will play a part sometimes in some of the ventilation. And again, relative humidity in a roof void and the external levels in the winter. These figures initially suggest a well-ventilated roof. Why? Because the external air is potentially sweeping out any internal air, and therefore they are very, very similar. The external conditions will be reflected internally in this roof void. But to nail this right down, you need other data. And again, similar effect in a subfloor void. The external in winter suggests that it's well ventilated. Very, very similar RH conditions. The external conditions are being reflected in the subfloor void because the air is sweeping through, and you're getting the same air effectively in the subfloor void as you are outside. But again, to confirm this or make other adjustments, you will need to have more data, the temperature data. Water vapor moves. Why? It exerts a pressure and will move down its pressure gradient. So, in the colder months indoors, there is more water vapor within a property. Why? Well, it's generated by occupation. So we've got more water vapor in a property than outside, and therefore it will move down this pressure gradient. It moves out through cracks and crevices and windows, but it also moves through the fabric of the building itself. But this is extremely slow. And if we look at why it's extremely slow, we can look at these figures. Vapor resistivity. The higher the figure, the greater the vapor resistivity. Look at the vapor resistivity of stonework. Very high to infinite. But notice the vapor resistivity of air is 0 and mineral fibre is absolutely minor. The other feature to bear in mind about these resistivity figures is that they are additive. So if we have 2 or 3 of those materials on top of each other, then we add them together and get far more vapor resistivity. We've had a look at surface condensation, but we also come across interstitial condensation. This is where the dew point is reached within the fabric of the structure. And there are 2 diagrams. Surface condensation in the top diagram, forming on the surface, and in the lower diagram, interstitial condensation. In this case, it shows it in cavity walls. In essence, is it really interstitial condensation, or rather just condensate on the surface of the outer leaf, or the inner surface of the outer leaf? But you can get it in solid materials, permeable solid materials. If we look at this, there's a wall temperature gradient going through a wall. But we can also calculate a dew point temperature gradient. Remember, dew point is the temperature at which condensation will occur. If the wall temperature gradient drops below the dew point temperature gradient, then we will get interstitial condensation. Interstitial condensation is most likely to occur where there is an external vapor check, which will even slow down or prevent the successful passage of moisture-laden air out through the wall, such as dense renders, impermeable finishes, and usually where there is a high internal moisture production. Well, interstitial condensation is not actually measured. It's usually the risk of it occurring that is calculated. It's not usually physically assessed. But we need to know the precise structure of the, let's say, a wall, for example. Once we know this, we need to know all the details about the wall, thickness and materials. The risk of interstitial condensation can be calculated. And data on vapor resistivity, thermal properties of materials and so forth are given in the British Standard below and a Building Research Establishment Digest 110. And what we finish up with is what we've just seen, and this is by this wall temperature gradient, dew point temperature gradient, and indeed where they cross, then theoretically there is a risk of interstitial condensation occurring. So we can summarize the following. Relative humidity is a proportion. That is a measure of saturation. It's not what one would refer to as an amount. For a given level of moisture retained in the air, the relative humidity will change with temperature. A high relative humidity does not necessarily reflect a high level of retained atmospheric moisture. It's temperature dependent. And we can go a little bit further and look at water vapor and vapor pressure, and put these into perspective in relation to relative humidity. Water vapor, as we mentioned earlier, exerts a pressure. That is directly related to the amount of water vapor retained in the air. The more water vapor, the greater the vapor pressure. In other words, it reflects, or it's a reflection of the level of water vapor retained in the air. Vapor pressure is not proportional to relative humidity. Why? Because relative humidity is temperature dependent. Therefore, for practical purposes, vapor pressure is not. It's measured as grams per kilogram of dry. So, if we look at these together, on the left we have our example of relative humidity as a proportion. But if we look at the example on the right, we can change those into, for example, vapor pressure. And just for convenience, we've simply called them units. So the one at the top now becomes 2 units, it's a measure, and the one at the bottom is now 1 unit. With reference to vapor pressure, it doesn't matter how big, for want of another words, the bucket is. Because if you took a 50-gallon bucket and put 1 litre of water in it, you've got 1 litre of water in a 50-gallon bucket. Double the size of the bucket, you've still only got 1 litre of water in it. And moisture production per day, average dwelling 4 to 5 people. Well, where they are, here we are, some figures. Total 14 to 17 litres per day. The only one I have disagreements with, or rather questionable, is washing clothes. I don't think that much water would come out of a washing machine. However, there we go, a family, 14 to 17 litres per day. Indeed, an individual can produce up to 9 litres per day. And we'll see this later on. So you'll now ask which is the dampest room, one on the left or the one on the right. Well, clearly the one on the left is. There is more water vapour in the atmosphere than there is in the room on the right. Going on with our water vapour, UK external atmospheric conditions vapour pressures. We've looked at humidities, but here are vapour pressures. This is the actual amount of water vapour that one would expect in the air. Note, there's a lot less during the colder months of the year than there are during the warmer months. Indeed, we can get down to 0.5 kilopascals, much lower on really cold, frosty days. And again, the external air temperature and vapour pressure. Again, in the winter, the colder it is, the lower the vapour pressures. The warmer it is, the greater the external vapour pressures. The other feature of water vapour, of course, it exerts a pressure. We mentioned that earlier. But it moves, therefore, down its pressure gradients. Let's take, for example, a kitchen. A lot of water vapour being produced in our kitchen. May not show up really, a bit of condensate on the windows, but it doesn't really show up because of the conditions there. However, it will follow its pressure gradient, and it can move around the house to areas of low vapour pressure. They may be significantly colder, and one finishes up with a problem well away from where the water vapour was developed. Indeed, you'll also find that wind direction will influence the movement of water vapour in a property. If we look now, carrying on with our water vapour, at internal and external environments, in an unoccupied house there's roughly the same level of water vapour in the property as there is outside. It comes into equilibrium. There's no water vapour being developed anywhere. There's a little difference in the vapour pressures between internal and external moisture levels. And one's got to remember that the total water vapour internally is the sum of internally generated water plus external water vapour. That is a sum. So we've got the external water vapour added on to what is generated internally. Hence we have more water vapour internally than externally in an occupied building. Again, considering internal and external environments, as mentioned earlier, almost all the excess water vapour in an occupied building comes from occupation activities. And during the colder months, there is inevitably more water vapour in a property than outside. There's less ventilation. Windows are closed, doors are closed, etc., etc. So, there is a difference, therefore, between internal and external moisture vapour levels. That is, internal minus external. This difference is very useful, and it is known as the differential or excess vapour pressure, and it reflects solely, this difference, the internally generated moisture, because from the internals we're taking away the externals. And one will find on cold winter days there's usually less water vapour externally, we saw that earlier, than on warmer days, and that leads to a drop in total internal moisture. So on the left we see on a warm winter day, on the right we have a cold winter day. The difference in total moisture is solely due to the external moisture levels, and this can significantly influence the internal levels. And remember, the differential vapour pressure, that's the difference between internal minus external, reflects the internal moisture production only. We also note that the internal vapour pressures are very dependent or related to the external vapor pressures. The external vapor pressure is a major driving force. Thus, if the external vapor pressure goes up, then so will the internal vapor pressure. Conversely, if the external vapor pressure goes down, so will the internal vapor. That will drop as well. So to summarize, vapor pressure directly reflects the amount of atmospheric moisture. It is not temperature dependent. Thus, for a given level of water vapor in the air by weight, the vapor pressure will remain the same, irrespective of temperature. The internal moisture vapor level is made up of the sum of the external vapor levels plus internally generated vapor from occupation activities. The internal vapor pressure is influenced by the external vapor pressure, and on average there is more water vapor in the internal air than external air during the colder months of the year. The difference between the two is known as the differential or excess vapor pressure. Snapshot measurements for basic environment and condensation assessment. A snapshot measurement is simply data taken at a point in time at the time of the inspection. In order to do this, we need to measure the temperature and relative humidity of the air. And to do this, we use a thermohygrometer. This will give us that data. Some also record the dew point temperature. When we've got our temperature and relative humidity, we could use a psychrometric chart to work out the dew point. And here's a psychrometric chart, and note that 100% relative humidity is where the air is fully saturated with water. So note the lines coming down from top right to bottom left. These are lines of relative humidity, 100, 90, 80, 70 and so forth. Scale on the right is relative humidity, scale at the bottom is temperature, and the scale on the left is vapor pressure. So let's imagine that the temperature and relative humidity we recorded were 60% RH at 20 degrees. There's our 60% RH line and 20 degrees at the bottom. Where those two meet, we put a mark. We then extend from that mark horizontally to the 100% line. That is where the air is fully saturated with water. It can no longer retain the water present. We then drop a line, vertical line, down to the base, and this tells us that the air is saturated at 12 degrees. That is, it is saturated at a dew point temperature of 12 degrees. Extend the line across to the left, the vapor pressure scale, and this tells us that the vapor pressure is 1.4 kilopascals. So we now know that the dew point temperature is 12 degrees. So what we have to do now is measure surface temperatures, and for this one can use an infrared surface temperature thermometer. If the surface temperature is above 12 degrees, then condensation will not be occurring. If it's below 12 degrees, then condensation will be occurring. Alternative to a psychrometric chart, one can use one of these sort of pre-prepared calculators. And this is quite a useful one, this Vaisala. Put your data in and it'll give you all the answers you want. But please note, condensation is an environmental event and must be determined by assessing the environment. One cannot identify the presence of condensation by other means. For example, looking for the absence of salts where a wall may be damp. So if we're using this basic methodology, one's always got to consider that condensation is frequently the result of excess internal water production and or reduced ventilation and or reduced heating. It is not the result of capillary bound moisture from damp walls, such as rising damp or floors. This, of course, excludes flooding, which is really an extreme. However, one must be careful of cold spots, which may exist in a normal ventilated, heated property. For example, very cold lintels or absence of insulation around the edge of a roof. A case study. This was a problem in a flat in London. The flat was part of a block, large block, and this was a ground floor flat. And the problem area was in the lounge, which was in the area of the north-facing wall. The case revolved around the fact that there was a claim that the property itself, namely the building, or rather the part of this flat's building, was damp. The building fabric was damp. And the case therefore was the plaintiff was blaming dampness in the walls that was causing her loss of clothing and so forth. So what did we see? Well, there's some mould growth. The problem that they were complaining about was in the lounge, the north face. And of course, they saw this tide mark. And what does one associate a tide mark with? Rising damp. So, let's have a look at this. At that time, it was distinctly wet and there were beads of water on the lower part of the north-facing wall. Probably been worse at some time previously. So here is the data we recorded in our snapshot. We showed that condensation was occurring up to about a metre on the north-facing wall. This was pretty obvious. The other feature we came across was the vapour pressures. The difference in vapour pressures, the differential vapour pressure, was 1 kilopascal, and that is massive. That is very, very high for differential vapour pressure. The next stage was to evaluate the north-facing wall. Now they'd noticed that this wall had been damp-proofed by means of an injection damp-proof, the holes being present externally. So the wall was profiled, that is taking regular samples up the wall, and the figure we were looking for was capillary moisture content. Capillary moisture indicates any source of water ingress. And indeed, in this case, it was dry. There is no water ingress at all. As far as the salts go, there was a salt band. This was at 1200 millimeters. That was typical of rising damp. But of course, the capillary moisture content showed the wall was now dry, so the damp-proof course had worked. Now, this gave them a bit of a problem, in as much as the wall was dry. So where was the water coming from? He had to find a source. That's the plaintiff's expert. So this is what he proposed. He proposed that the water was coming from the junction, the floor wall junction. We know the wall was dry. It was monitored and evaluated. So he's now claiming the floor was wet. Well, this was set under plastic tiles, and it was also below the dew point. But he was saying water was evaporating from a position where it should be condensing, escaping through this very narrow gap, and then condensing further up the wall. Well, this is total nonsense. However, water evaporates from a saturated screed at room temperature at a rate of about 75 grams per day for a 16 square metre floor. And indeed, a wall is no different. However, air movement may increase this figure. An average individual, their lifestyle, can produce up to around 3.5 litres of water per day, i.e. 3,500 grams of water, to excess of 9 litres per day. That's in excess of 9,000 grams of water per day. Therefore, the origin of the water causing the severe condensation was the plaintiff's lifestyle. It was not dampness from the building fabric. That was shown to be dry. So, in summary then, a snapshot investigation only records the conditions at the time of the inspection. Atmospheric conditions change rapidly over short amounts of time. The snapshot may not reflect the longer conditions that are causing the problem. For example, the conditions occur at other times. Water vapor evaporating from capillary-bound moisture in damp substrates, such as rising damp, does not add substantially to the overall moisture burden in the internal atmosphere. But this does not include excessive or free moisture from flooding. And finally, water evaporating from a damp substrate may increase the moisture burden where it evaporates into a very restricted space, such as into a small volume, such as behind a hanging picture or into a cupboard, some isolated area. Long-term monitoring of the internal environment and assessment of collected data. Well, the previous methodology we've just looked at will only give us a snapshot of the conditions at the time of the visit. But frequently the conditions that are responsible for the problem will occur at times other than the time of the actual inspection or survey. It therefore becomes essential to monitor the environment over a period of time to assess the long-term changes in conditions. We can do this by means of specialist data loggers. These are temperature and relative humidity data loggers, and they also record dew point temperature. The data from the logger is presented in this form, and note that the data is in text format. And we can produce that data simply from the program that is supplied with the loggers, and here's an example. It gives us the red's the temperature, the green is the dew point, and the blue is the humidity, and the scales are on right and left. But in this case, also note the variations with time. Somewhere it's going up and down like a yo-yo. Where do we place data loggers? This is actually quite important. If we look at them indoors, keep away from heat sources, radiator lamps and fires, away from windows, try to keep them over 15 centimeters away from a wall surface, and place where the airflow is not particularly restricted. Outdoors, try to keep them away from direct access to elements, rain, snow and sun, and position to allow good typical airflow. In this particular case, we have found it very useful to hang them in polystyrene cups with holes punched in the side. They act somewhere like a bell clanger. We can use them quite simply to assess the long-term temperature and humidity. And in this case, note that humidities over 80% lead us with a mould risk to items within the room. And we'll be dealing with this under mould growths. So a summary then. Data is recorded in text files. Data can be expressed graphically in the provided software, and recording can be given precise start points. Intervals between recordings can be adjusted, for example, every 15 or 30 minutes, 1 hour, whatever one wants to set. We find it most useful to use 30 minutes. However, the text data from loggers can be converted to vapor pressure and more, so we can manipulate the recorded data in various ways via spreadsheets. Turn the data into vapor pressure, and then this can be used to produce what is known as differential vapor pressure or excess vapor pressure, and that is the difference between the atmospheric moisture levels internally and externally, and it's very good at looking at factors such as performance of ventilation. And here's just an example of differential vapor pressure during the summer. Don't usually do this sort of stuff during the summer because we have good ventilation with doors and windows open, but it does illustrate a couple of items. On the left we have positive and negative vapor pressures. Where it's positive, we've got more water internally in the atmosphere than outside. But notice how the data, vapor pressure data, goes up and down, positive to negative, all the way through the summer, and it does this anyway. And also notice that the average trend, whatever you want to call it, is 0. Why? Because the windows and doors are open, we're getting good ventilation overall, but notice the variability, this constant variability, but we have an average. The other interesting point to note is at the right hand side, all of a sudden, or we start getting vapor pressures always in the positive. Why? Because it's getting colder and the doors and windows are starting to be closed. Following monitoring of properties with no known damp problems and considering an internal relative humidity at 20 degrees, a differential vapor pressure of up to an average of around 0.45 to 0.50 kilopascals might be regarded as acceptable during the colder months of the year, but certainly not during the summer. But in looking at this, there may be other factors to be considered. Again, differential vapor pressure during the summer. This was due to poor ventilation. As mentioned earlier, we don't normally look at vapor pressures during the summer because the windows and doors are open and they're not really going to tell us much. But in this case, the client, housing association, had a lot of problems with a tenant claiming the building was damp. So in essence, we were forced to do this for them. And the average expected ventilation in a property in the summer would probably not be much above 0.2 kilopascals, a differential vapor pressure above 0.2 kilopascals. But look at this lot. They're getting a problem even for winter levels. The ventilation, they just weren't ventilating, the fans never worked in the bathrooms and so forth. But the walls were absolutely bone dry, and all the client was responsible for was indeed the fabric of the. Another one, long-term monitoring, differential vapor pressure. Look what happens. There's a problem when there's occupation. When no occupation, in other words, when they went away for Easter, for example, then we had no problem. The differential vapor pressures dropped to 0. There was no excess internal moisture production. Again, nothing to do with the fabric of the building. It's an occupation problem. Another differential vapor pressure in a flat. Again, you can see the difference between not occupied and occupied. The minute the individuals leave the property, then the problem effectively disappears. You can see that when it was not occupied, shown in green. Rather an interesting one. This is the raw data from a data logger. Relative humidity. The scale is on the left. Temperature scale on the right. Looks interesting, but what was happening in the middle? Got this up and down movement. Nothing really specific about the relative humidity in the lounge or the bedroom. So what was going on? Well, we converted that to differential vapor pressures, and it becomes quite clear something was going on. What would happen? Well, the landlord subsequently reported that there were 2 areas, or rather 2 time periods, when the property was not occupied, or rather the flat wasn't occupied. But when the flat was occupied, then we had a significant problem. Again, it was an occupation problem and not dampness within the fabric of the property, as often claimed. Again, influence of the external vapor pressure on internal vapor pressure, and this is quite important. Note this influence. The external vapor pressure drops, so will the internal vapor pressure. We mentioned this again earlier on in one of the previous presentations. But it will drop. The external vapor pressures have a significant part in relation to the total moisture vapor in a building. Effect of subfloor vents on ventilation. It was said that subfloor vents were not effective. So we tried this by measuring things and opening and closing vents. Notice how the differential vapor pressure went up when the vents were closed. Open, it went down. Closed, it went up. Open, down. Closed, up. What was happening? When the vents were closed, there was no ventilation, pretty obvious, but when it was open, we were getting ventilation, and the moisture-laden air in the subfloor void was being swept out. When they were closed, we were getting additional moisture vapor being added from the room above. Very useful methodology, long-term monitoring. And we can also look at moisture in solid floors and walls, and we can do this by using these little hygrometer boxes, and it compares the water vapour emanating from the floor, or we could use it for a wall, with that of the room. We're looking at the different vapour pressures. And indeed, once this is on the floor as a closed hygrometer box with a data logger on top, if the vapour pressure is greater in the floor, i.e. where it's trapped under the box, then the floor is damp. So if the vapour pressure is greater in the floor, then the floor is damp. That is greater than what's in the room. It's quite a good method of checking floors. So then, to summarise, differential vapour pressure can be used as an extremely useful long-term guide to assessing ventilation and moisture production, and in many cases it is essential. A differential vapour pressure of up to around 0.5 kilopascals might be acceptable in living areas. Other data, of course, might be required. External vapour pressure is influenced by external temperature, and therefore internal conditions can be influenced. Long-term monitoring wall surface temperatures. This is the equipment, wall surface temperature equipment, and there it is at the top. That is the whole gear. On the bottom is the actual monitoring, the data logger. See how small it is, and quite simply it's stuck to the wall. It's loaded into the receiver at the top at the end of the logging, and the data is removed, and we get the temperature data for the surface of the wall. And it's interesting looking at the relationship between air and surface temperatures. We can see here from these two with constant heat and intermittent heat how rapidly the surface temperature of the wall, that is in red, follows the changes in the air temperature. It's extremely rapid. Therefore, raising the room temperature will raise the wall temperature. And if we do that, the warm surface also lowers the relative humidity in the boundary layer of air, and so lowers the risk of mould growth on that surface. Again, if we look at the internal air and wall surfaces in a real situation, then we can see there is this rapid change. This is marked by means of those arrows just to illustrate it from this set of data. When the air temperature goes up, the wall surface temperature goes up. Conversely, when it goes down, the wall surface temperature goes down. A direct relationship, and it's very rapid. On the other hand, if we have a look at the influence of external temperatures on internal wall surface temperature, the effect is far, far slower. There is no direct relationship, or rather quick direct relationship. What we have is a much, much slower change, as we can see from the graph. The arrows are showing quite simply that there is no rapid change with change in one factor or the other. So it's a much slower change when we're dealing with outside temperatures. This is the effect of improving airflow behind objects. Again, it's illustrating how the air temperature influences surface temperature. On the figure on the left, there was a piece of furniture in front of the wall on a very cold period of time, and we can see that the surface temperature where that piece of furniture was is around 8 degrees colder than the rest of the wall. However, take it away, let some air start moving, and we start to get an improvement after removing the furniture. Airflow is now influencing the surface, and it's not, for want of another word, the coldness in the wall itself. The air temperature is wall. If we know internal temperatures, relative humidities, and the dew point of course, and wall surface temperatures, we can compare the surface temperatures with the dew point temperatures. So here's an example. On the left we can see the scale. If it's below the dew point, it's a minus number. But in this particular case, we can see that condensation was occurring most of the time. That surface was only out of condensation a very small amount of time. In other words, it didn't come above the dew point for very long or very often. And another thing we can do is calculate the surface relative humidity. So let's say the room is 60% relative humidity at 20 degrees and the wall temperature is 14 degrees. So where the two meet, or rather the 60% and 20 degrees centigrade meet, put the mark as usual. But then what we will do, we will raise a perpendicular from the 14 degree mark at the bottom, the surface temperature of the wall, to meet our horizontal arrow. And where those two meet, in this case, it gives us a relative humidity at the wall surface of 90%. So at 14 degrees, the relative humidity would be 90%. And this is certainly sufficient enough to allow certain moulds to grow, as we will see later, if it remains static. The other factor one can look at is intermittent condensation, and this is the principle. On the bottom we can see we have occupation and heating on, occupation and heating off at night, and occupation and central heating on in the morning. So we start off by the wall surface temperature. We know the wall surface temperature is influenced by the air temperature. We now have atmospheric moisture levels. And in this case we can see that the temperatures are dropping quite rapidly once the heating is off at night, but the atmospheric moisture levels dissipate far more slowly. And it's usually at that point we will get our problem, say perhaps between 2 and 3 in the morning. And this is how we get this intermittent condensation. And of course we can only see this if we do long-term monitoring of the atmosphere and temperatures and so forth. And we can get pretty large differences between the internal air temperature and wall temperatures. And on the right there shows some of the differences. The left figure is from the upper area of the wall. The right hand figure in the final column is the lower part of the wall. We can see temperature difference between the air temperature in some of these areas of 6 to 10 degrees. The high ones are marked in red, but you can see there is some considerable difference in places. And this is one of the effects of that. The lower part of the wall was dropping below the dew point in these flats, and one can see the condensate forming on that wall. Above that height, about a metre in this case, there was no problem. The wall was sufficiently warm to keep it above the dew point. So, to summarise, wall surface temperatures are rapidly and significantly influenced by internal air temperatures. Raising the internal air temperature will raise the surface temperature and therefore lower the relative humidity in the boundary layer of air. And of course this can help lower the risk of condensation and mould growth. And indeed insulation will help in many poor cases. Restriction of airflow to external walls will cause their surfaces to cool or be cooler, simply because we lose the influence of internal air temperature. This can raise the relative humidity. The cooling will raise the relative humidity in the boundary layer of air significantly, and this therefore increases the risk of condensation in such positions and mould growth. The importance of relative humidity. When one is dealing with the internal conditions in a building, it's effectively relative humidity that is the major factor. Why? Because It is this that potentially leads to health problems, especially related to dust mites, mould, bacteria, viruses and so forth. It is what we could call loosely a damp environment. Mould growth can occur on certain moisture-sensitive materials, such as leather, cloths, wood, and they do this by maintenance of relative humidities simply in excess of 80%. High relative humidities also lead to an increase in other items which have been implicated in health problems such as dust mites, bacteria and viruses. And of course, surface temperatures of walls and other cold areas, such as behind cupboards and so forth, will inevitably be several degrees lower than the room temperature. Thus, the relative humidity in the boundary layer of air against such surfaces will then be in excess of 5 to 15% higher, occasionally even greater. And of course, a cold environment will lead to higher relative humidities under what we would regard as normal airborne atmospheric moisture levels. These will then add to a risk of mould growth, plus the other agents such as dust mites, which can occur in such situations. If we look at properties, we found that analysis of a number of what we could loosely call non-problem houses in living areas showed that during the colder months of the year, around 60% RH as an average, and that's important, and less are achieved. Therefore, a practical method of making an assessment is to make an assumption. That is, to assume the internal occupied areas are comfortable and a constant 20 degrees. If, after this assumption, the relative humidity is, on average, much above 60%, then ventilation is needed. If, after this assumption, on average, it drops below 60%, then increase in heating is required. However, you need to assess this over a period of time. It's important to note that in a cold environment, by raising the temperature, we can reduce the risk of mould, dust mite, and so developments, as this will lower the relative humidity. And this diagram illustrates this, as we've illustrated it previously. 14 degrees at 80% relative humidity, we would have a risk of mould. However, if we can increase the heat to 20 degrees, the relative humidity drops to 50% and the mould risk is gone. This was a case study, and it was cold in the house. The actual temperatures were between 12 and 18 degrees. So we recalculated these conditions, and this now assumes the temperature was raised and maintained at 20 degrees, and we finish up with the graph we can see. But even doing this, raising the heating to 20 degrees, the relative humidity would still remain high. You can see this on the left side of the graph. It's averaging 70 roughly. But what's happened on the right hand side of the graph? There has been a drop in external moisture levels, and this has caused a drop in internal levels of atmospheric moisture, and hence a drop in the relative humidity. So if we look at these figures overall, especially the first part on the left, more ventilation is needed to reduce the relative humidity, as well as some possible slight better heating. We noted in the previous property the internal relative humidity dropped during the colder weather, solely due to the external water vapour levels dropping. This clearly shows the importance of the effect of external environments. And we saw this in a previous presentation. In a warm period, we've got internally generated water and externally generated moisture. That is the total moisture. Add those two together. Whereas in a cold period, we actually lose a proportion of the external moisture. There's less moisture in the atmosphere when it's cold than when it's warm. and thus for a constant temperature the relative humidity in the property would fall. And that is why it is essential to monitor external conditions, because this can significantly influence the internal relative humidity. Therefore, we really need to do this over a period of a minimum of 2 weeks, as long as 4 weeks, if possible, even longer. There's another case study. This was a kitchen. The lady was getting mould in the cupboards, and this was the result that we had from monitoring the kitchen and the cupboard temperatures and relative humidity. Note the very high relative humidity in the cupboard. Also note at the bottom, the green line, how low the temperature was in the cupboard, about 10 degrees lower than it was in the kitchen. So what we did, we recalculated these figures, assuming a constant 20 degrees in the kitchen and in the cupboard. So when converted to 20 degrees, the relative humidity in the cupboard and the kitchen are similar. We can see that on the graph. The high relative humidity in the cupboard was solely due to very low temperatures, and it was nothing to do with dampness in the rear wall. We can also compare the vapor pressures in this case. In this case, we are comparing internal with internal, and again, we can see that the vapor pressures are very, very similar. So we have the same amount of water vapor in the air, in the kitchen and in the cupboard. So again, there is no extraneous source of water being added to the cupboard. The mould was simply due to the very high relative humidity due to the very low temperatures in the cupboard. It should also be considered that different materials vary in their ability to transmit heat. For example, dense materials, glass, steel and so forth, transmit heat well, whereas the more open materials such as polystyrene, fiberboard, etc. do not conduct heat well. And it's why these materials make good insulation, because they can maintain a good temperature differential between the warm and the cold. Again, looking at a property, the coldest areas are usually on north-facing walls, possibly east-facing. These walls are most likely to be at risk to surface condensation. On west to southwest walls, dampness could be water penetration, especially through cavity fill. In most parts of the country, it is the southwest walls that are subject to the weather and the wind. And of course, thermal bridging can occur in areas such as metal window frames, concrete lintels and doors, etc. However, it is very important to appreciate the surface temperature of walls and other cold areas behind cupboards and other restrictions, wardrobes, will inevitably be several degrees lower than the room temperature, and then the relative humidity in the boundary layer of air against such surfaces will be in excess of 5 to 15% higher, sometimes as much as 25% or more. And a cold environment, as we've seen previously, will almost certainly lead to higher relative humidities under what one would regard as normal, reasonable airborne atmospheric moisture levels. When we get these factors, they will lead to a risk of mould growth, and indeed the other agents we've mentioned occurring in such conditions. So to summarise, the relative humidity will be higher in a cold internal environment than a warm one under the same conditions of occupation. Relative humidity is important in that where it remains suitably high, it can result in mould growth and proliferation of other microorganisms. Relative humidity against external walls is higher in the boundary layer of air, that is, air in direct contact with the wall, due to such walls being colder than the internal air. Internal assessments. If we're going to undertake environmental moisture assessments, the first thing we need to do is there's the visual assessment. And this is of course undertaken at the time of the and visual evidence of dampness. Well, there's a simple comparative table. I'm not going to read it, but you can read that for yourselves. It gives you all the differences between condensation, rising damp and penetrating damp. And of course, condensation is effectively seasonal, most commonly between September and April. So what do we do visually? Well, water droplets on impervious surfaces, glass, paint, tiles, plastic wallpaper. Impervious surfaces show the condensate up as liquid water. It's come off on your hands. If the surface is permeable, such as some plasters and so forth and paper, you may not see it to start with. It doesn't particularly look damp unless it gets very severe. In this case it was severe. Here it is on paper, the lower part of a wall. That area up to about 1 metre was below the dew point, and it occurred in all the flats. More visual assessment. It's a bit of a serious one, this one, but there's plenty of water around to see, caused by surface condensation. More here. Quite interesting, this one. On the upper left we have a photograph that's lining paper, distinctly wet. Indeed, there was water running down the wall, but virtually no mould. And the photograph on the right shows condensate on the base of a party wall, which is pretty extreme. Fairly obvious again. There's some water run marks above the window, and somebody in that place smoked. Here again, the 4.5 inch part of the wall, that was condensate soaking into the finishing plaster. It did not occur on the thicker part of the wall. Corrosion runs past nails. All of these are obvious signs of condensation and water running. Subfloor condensation can be very serious, often a cause of dry rot, lack of subfloor ventilation. And this is rather an interesting one. It's the effects of cold mortar beds in the gable end of a roof. The condensate was forming onto the colder mortar and soaking into the lightweight blocks. More condensation, been condensating on the lining and then soaking into the timber. So those are the visuals. The next thing one needs to do is to collect information about the property, building itself, ventilation, number of occupants, times of occupied, insulating, heating, history of the problem. And then we start recording data. We can record data at the time of the inspection, surface temperatures, air temperatures and humidity, inside and out. Recorded data. This was from a snapshot. We've got this data. We've measured the air temperature, relative humidity and vapor pressures, and we have the wall surface temperatures and the calculated relative humidity at the surface temperature. Notice at the base of the walls it's getting over 70. In one case, in the bedroom, it was over 80. Why? The base of the walls are colder. We can see that from the wall surface temperatures. So, and the vapor pressure, we see at the bottom, differential vapor pressure, internal minus external, was very good. It was 0.39. But again, I'll emphasize again, note the elevated relative humidities of surface temperatures at the base of the walls. They are colder, hence the relative humidity. We can collect long-term data, temperatures inside and out, relative humidities inside and out, wall surface temperatures, and we've seen how to do this earlier on. And we need to analyze the data. It needs to be appropriately manipulated. For example, this is just a straightforward temperature humidity in relation to a room, bedroom I think in this case, yes, and mould risk to exposed goods such as leather and cloth, because we were getting mould growth on the bedclothes. But look at the relative humidity, it's running up around about 90%. That will allow mould growth on certain items and certainly on certain cloths. We can do differential vapor pressures, which we've mentioned earlier on. This case it's very high. We would expect an average of about 0.5. That's the maximum expected average, but in this case it's running much higher. It's running up about 0.7. So we have a ventilation problem. And again, relative humidity at the surface temperatures. Remember, surface temperatures of walls are usually colder, and we have here risk of mould to the surface in the external wall. RH is running again somewhere just below an average of 90. However, if we take the internal wall, the relative humidity is down just below 70. It's much warmer, and we can see that from the temperatures as indicated in red and black, or rather red and green along the bottom. And once we've got all this information, visuals and so forth, we collate all the data, including your visuals, and make your conclusions and recommendations. So what about relative humidity or vapor pressure? Well, we use relative humidity for condensation assessments, internal environment assessments, risk of mould, moisture in timber. Remember, timber is a hygroscopic material. It absorbs atmospheric moisture quite readily, and indeed hygroscopicity as a whole. And here I'm really thinking about salt damp caused by hygroscopic salt contamination. We can use vapor pressure or other factors, absolute humidity or mixing ratio, to assess the potential change in the internal environment over a period of time. And we could also use it in some cases to determine what is dry after flooding. Moulds and the development of mould growth. There's some moulds. Notice quite heavy mould, different colours. There's black mould there, there's these yellowy sort of ginger mould, there's actually some green mould if one looks at the colours very carefully. But where we go is we have distinct variations in colour depending on the species. And again, it shows up much better on this mouldy ice cream that was left out. We have yellow moulds, blue-green, white, black, pink, different colours of mould species. More mould, black mould, typical triangular pattern in the corners where the air is very stagnant. Cold patches, cold spots. Window reveal, commonplace. Over a cooker. And this is where somebody was breathing on the wall where they slept. And finally, with reference to this is missing insulation around the perimeter of a room, and the temperatures show where the insulation is missing. This is a black mould. It's actually developed beneath wallpaper. You can see the staining on the surface, but the mould itself is under the wallpaper. This is caused by a wet wall, not by condensation. Again, similar pattern caused by dampness within the wall itself, not condensation. Sometimes one may come across this. These are houses 10 years old. You can see the lightweight block, or rather the outline of it, in the mortar beds, and it's known as grinning or pattern staining. The mortar beds are, in this case, about half a degree cooler than the block itself, and when one does a tape lift, there's no mould there, it's purely dust. Indeed, the surface temperatures here were always 4 or 5 degrees plus above the dew point. It is simply dust. Why it collects on the colder spot, I don't know. But here's just the example, looking at a thermal image of this. It shows up the cold spots. So back to moulds then. There are over 100,000 species of mould worldwide, but less than 100 are common in the UK. The most common being Penicillium and Cladosporium species. Stachybotrys shatarum, a so-called toxic mould, is uncommon but not rare in the UK. So the basic features of mould: they have simple food requirements, and like all fungi, they produce vast numbers of spores, and they can grow quickly under suitable conditions. In other words, we can regard them as very much opportunistic. They have the same requirements for growth and survival as rots, or indeed any other fungus. They require oxygen, air, suitable temperature, nutrients, and moisture. Moisture is really the only effectively controllable factor. And the requirements for mould growth on a particular substrate depend on water activity, or hygroscopicity of the substrate, airflow, and of course relative humidity. The life cycle of a mould is very simple. We start off with a spore. These are floating around in the atmosphere and they can be very, very high in number. Simply float around. If they land on a suitable surface where the conditions are right, they will rapidly germinate, produce these hyphae, thin filaments, and we get a mass of these where they become known as the mycelium. Within the mycelium, the fruiting bodies or sporophores develop. These contain the spores and these are effectively budded off and get carried away around in air currents. Here's some spores, Getomium species and Cladosporium species. Cladosporium is a common black mould, and sometimes I believe it's referred to as the king of the black moulds. That's Cladosporum cladosporoides. Occurrence of moulds in buildings. This was published in International Biodeterioration Bulletin and some research done at BRE. And you can see the common ones: Aspergillus, Cladosporium species, Penicillium species. Large numbers, percent in all dwellings sampled. And again, those species are present in the air. The other two, the Stachybotrys and Fusarium, are not particularly common in air. And one should always consider that microbial contamination in buildings can vary greatly. And notice its presence in a building alone does not constitute exposure. It is important, however, to note that the long-term maintenance of high humidities, we're talking here in excess of 80%, without condensation, causes moulds or some moulds to develop in stagnant areas, especially on moisture-sensitive materials such as leather, some cloths and paper. And what species of mould grows where depends on a number of factors, but especially the humidity and the particular substrate. And of course the colour of mould will depend on the particular species. And this shows up the different colonisation of moulds. They can be split into primary colonisers, requiring RHs of up to about 80%, 75-80%. Secondary colonisers, they will germinate and require 80 to 90% RH, and the tertiary colonisers 90% plus. So we have this different requirements for different levels of colonisation. And it's highly likely that much of the mould in buildings does not require condensation. It develops via these primary and secondary colonisers due to very high humidities developing. And here's some examples. We've got wood and wood-based materials, 75 to 80%, so we can get the primary colonisers on these. Similarly on paper and plasterboard, secondary colonisers, mineral insulation materials, secondary and tertiary colonisers, extruded polystyrene, tertiary colonisers more or less, concrete, tertiary colonisers. It depends on the material. And this is a good example of mould on leather due to maintenance of high humidities. This was a wardrobe, it was monitored, there was no condensation anywhere in there. High humidities were high, simply it was so cold. And in this case, the mould developed on the leather, notoriously susceptible to moulds, and it never developed on the clothing. It never developed on the clothing, purely as a result of the very high humidities being developed in it, simply due to it being very cold. Rather an interesting case as well, mould bloom on a party wall. Again, it's resulted from persistent high humidities, and the arrows show this bloom. Interestingly enough, nothing showed even on the corner of the right-hand wall. It was that particular wallpaper that showed all this bloom. Condensation never occurred on that wall. And again, mould caused by maintenance of high humidity. There's the photograph. Mould only developed on the moisture-sensitive board on the back of the unit. It never developed on the painted wall where condensation actually occurred. And this was simply caused by the high relative humidity which developed in the cold stagnant air behind it. And this is the actual data from there. Note the wall behind, in green, dropped below the dew point, hence we got condensation periodically. The back of the sideboard never did, or the back of the unit never did. And this is where the mould grew, because that particular material was susceptible to mould, and we're probably looking at primary or secondary colonizers. And again, a similar factor. This was mould on the back of a picture. It had developed on that picture simply because that material was particularly susceptible to mould and very high humidities were present in that room. So then, to summarise, many moulds found in houses do not require surface condensation for their development. Primary and secondary colonising moulds only require relative humidities maintained in excess of 80% to develop on certain moisture-sensitive materials. Toxicology and Mould, an introduction. The following presentation is taken fundamentally from published research papers, and these are listed. So let's start with toxicology. Paracelsus, sometimes called the father of toxicology, wrote, "All things are poison, and nothing is without poison. Only the dose permits something not to be poisonous, or more commonly, the dose makes the poisonous. That is to say, substances considered toxic are harmless in small doses, and conversely, an ordinary harmless substance can be deadly if overconsumed." And I've used aspirins. So what is a hazard? A hazard is the ability to cause harm or adverse effects. Basically, what is a risk? The likelihood that a hazard will actually cause you harm. For example, cyanide is a hazard, but the risk of it causing harm when in a stoppered, break-proof bottle is effectively zero. So what are the factors that influence the degree of risk? How much a person is exposed to the hazard, this thing or condition? How is the person exposed? And how severe are the effects under the conditions of the exposure? And again, we come back to our aspirins. So in order to effect a response, an individual must be exposed to the substance or the organism, such as in a house, mould, dust mites, volatile organic compounds, all kinds of stuff that one finds in the domestic environment. And the dose is determined by the degree of exposure, that is, time and amount. The presence of the agent in a building does not necessarily constitute exposure, and any exposure may be below the no observable effective level. Therefore, the degree of risk when exposed to a hazard will vary. Toxicity in the absence of a quantification of risk is meaningless. As we mentioned earlier, a material could be the most toxic substance known to man, but if the exposure and or risk is vanishingly small, then does it really matter how toxic it may be? And that's a question. Focusing on toxicity, irrespective of risk, leads to the presence equals significant exposure. Exposure equals significant dose, and significant dose equals illness. Therefore, presence equals illness. So what are the potential health aspects of mould? Well, toxicosis. Some fungi produce toxic substances called mycotoxins. These are toxic secondary metabolites present in fungal spores and hyphae. And of course, moulds produce a large number of volatile organic compounds, and this gives them their typical mouldy odour. We now come to the term toxic moulds. This term was given by the media. It is not actually a scientific description. There are 4 species of moulds that are considered to be in this group. Stachybotrys shatarum, or Stachybotrys atra. It's a brown-black mould that grows on cellulose substrates. It's very slimy, and it requires very wet, damp substrates such as following a flood. In other words, it's a tertiary colonizer. Penicillium species, some of those are considered. Aspergillus species as well, some of them. And finally, Fusarium species, some of them. So what are the detrimental health effects due to airborne moulds? Well, there are proven health effects. Most of these are from agriculture or occupational exposure. There's irritation of eyes, nose and throat, dermatitis, exacerbation of asthma, not its cause, allergy, probably the most common, and aspergillosis, also known as farmer's lung, and it usually affects immunosuppressed individuals. These are the ones that are at risk. The reported health effects, not proven: fever, flu-like symptoms, fatigue, coughing up blood, nosebleeds, dizziness, headaches, diarrhea, vomiting, and liver damage. So, what about exposure to moulds? Outdoor mould levels. Well, all one has to do is pass a field where they are haymaking during the summer and then measure moulds in the atmosphere there. But here's an example: seasonal variation in outdoor mould spore concentrations. And we are looking here at spore numbers at times of 50,000 in the sheltered areas, and even in the unsheltered areas or exposed areas, they're 25,000 spores per cubic metre. You don't get that in a building. Occupational exposures, another here. Wood yards, 10 to the 6 to 10 to the 8. That's 1 million to 100 million spores per cubic metre. British farms, 1 million spores per cubic metre. Potting sheds, taking another one, 7,500 spores per cubic metre of Stachybotrys shatarum. These are pretty huge numbers. And by simply throwing a mouldy orange in a bin, there was a paper showing that over 200,000 spores per cubic metre were left in the air. So let's look at some of the references. German Mould Guide. Very rare and almost exclusively occurring in the workplace is extrinsic allergic alveolitis, which is generally produced by repeated exposure to very high concentration of spores, that is 1 million to 100 million, which cannot be expected to occur in residential properties, basically. And anticipated systems by atopic persons. Atopy is a predisposition, get it right, towards developing certain allergic hypersensitivity reactions. So there we go. Look at the spore counts and the results. These are from people that are sensitive to these things. And this data comes from the American Academy of Allergy and Immunology. Mould Facts for Patients, excellent piece of work, extracted from Professor Richardson's Mould Facts, Mycology Reference Centre, Manchester. Again, moulds on the left, and what do we say for the health risk? Potential allergy, immunocompromised for Aspergillus fumigatus. Again, going down the list, we can see opportunist, and toxins and human health, no conclusive evidence frequently. Alternaria, toxins listed, Fusarium, toxins listed, and Stachybotrys shatarum, toxins listed and actually produced. quite the information. Where do these come from? Indoors. It's got a list there of where we get them from. All environmental moulds can, but not necessarily do, produce mycotoxins. Again, more quotes. This is basically the result of the WHO, World Health Organization, and the Institute of Medicine in America. It says, in that study, the IOM stated there was insufficient evidence to find a causal association between the presence of moulds and any of the claimed adverse health effects. That is, after reviewing the global and scientific medical literature, the IOM could not find sufficient evidence to support the argument that the normal presence of mould in residence and workplaces caused any adverse health effects. And again, they are consistent with other organisations and authorities. Health Alert, published by University of Health and Johns Hopkins Medicine. Again, it says it is highly unlikely that you can inhale enough mould in your home or office to receive a toxic dose. Goes back to our dose equals amount plus time. Sick building syndrome. Again, here we go. This is from Mycotoxins, a journal. There is no evidence that mould presents an imminent threat to life for healthy members for typical indoor exposures. The concentration of mould contamination required to create infective doses is improbable and inconsistent with the reported spore concentrations in buildings. Current scientific evidence does not support the proposition that human health has been adversely affected by inhaled mycotoxins in home, school or office. Again, American College of Occupational and Environmental Medicine Council, evidence-based statement. Finally, it's the same arguments and the same information with reference to guidelines, New York City Department of Health. That's their views based on data. So, the mere presence of such a mould should not be taken as evidence that the mould was producing any mycotoxin. For a toxic effect to occur in a subject, the toxin must be present, there must be a route of exposure, and the subject must receive a sufficient dose to have a toxic effect. So what do we conclude? Or at least from the Journal of Allergy, Clinical Immunology, the occurrence of mould-related toxicity from exposure to inhaled mycotoxins in non-occupational settings is not supported by the current data, and its occurrence is improbable. More again. 2 reviews. Health risk of dampness or mould in houses. One review concluded that combining the elimination of moisture intrusion leaks with removal of mould is effective in reducing allergy, etc., etc. And the other one again, there was moderate evidence of remediating dampness and mould problems in houses. So we can see where we're going with these stuff in removing dampness. So therefore, based on peer-reviewed documents and literature, the fundamental problem is a long-term damp environment. It is these long-term damp environments that give rise to moulds and dust mites and the rest of these items. All these are associated with a damp environment. Toxic moulds are therefore certainly nowhere near as devastating as some of the media and some individuals would have us believe. They're only likely to affect sensitive, i.e. atopic, and immunosuppressed persons. By far the greatest proportion of the population will not be affected. So the evidence so far, that is the published evidence from science and medicine, suggests that moulds as an individual component in a damp internal environment are unlikely to affect healthy individuals. It has been concluded that there was an association between damp living spaces and some adverse health effects, but no one's been able to demonstrate conclusively that the association is exclusively due to the presence of mould. There's a whole mixture of items in a damp environment, and as such, the stress is placed on correcting the damp. We mentioned the word association. What do we mean by an association? Well, it's the weakest of all epidemiological evidence. What it means is simply an observation occurs with another observation without further quantification. For example, the last person who lived in this house died of lung cancer. The last 5 occupants of this house died. Fact, occupancy in the house is associated with death. Fallacy, this house is causing people to die. Fact, virtually all people who have died have lived in a house. Absolutely all people who have lived in a house will die. Association is the weakest of all epidemiological evidence. So to summarise then, whatever the case, the risk of health problems is greater in a distinctly damp environment than a dry one. It is essential to get the building back into a suitably dry state, irrespective of how the occupants review it. Control of atmospheric moisture and mould growth. There is broadly a condensation season. This is generally between September and April. If there is dampness outside that period, it is probably not condensation. There are basically 5 major factors that need to be investigated. Ventilation. Is it adequate for the occupation and volume of the property? Similarly, is the heating adequate? How is it being used? Moisture production. Is it reasonable, given the variation in lifestyles? Are there possible excesses, for example, drying clothes? Airflow. Movement around and behind furniture. Is it adequate? Insulation. Are there specific cold spots? The above are usually grouped together, generally, as lifestyle, that is, the effects of occupation. So what is lifestyle? Well, for our purpose, it's water generated by occupation. A domestic property should be able to cope with this, or rather a normal lifestyle, that is, with normally accepted activities, no overcrowding, no unrealistic moisture generation from bottled gas heaters, drying clothes, etc. And if we look at it, there are 2 extremes of normal lifestyles. Family 1 has cereal for breakfast and salads, tea, etc., with minimal cooking and mostly out all day. Family 2 all have cooked breakfast, fully cooked dinners in the evening, young children, and some occupation all day. The property should be able to cope with both extremes by one means or another, and appropriate systems should be in place to allow this. The average domestic property is not designed to manage additional extraneous sources of water, such as from paraffin heaters or continual use of unventilated dryers. So back to control of atmospheric moisture and condensation. Improve ventilation. What are we doing? We are sweeping out moisture-laden air and replacing it with drier air from the outside. In reality, however, we don't totally replace it. We are effectively diluting it with dry air. And this is the theory of ventilation. Perfect ventilation would throw out all the internal air and replacing it with external air. So we'll have the same amount of air outside as inside. No ventilation, internal vapour is significantly higher than external because it's not being swept out. In reality, we could call it ventilation. Internal vapour is higher than the external, but at an acceptable level because it is being diluted and partly thrown out by means of the external air. Typical ventilation rates as a whole system there from well-sealed dwelling in shelter position to leaky dwelling in exposed position, and they're from BS 5250. Ventilation again, fans, manual or humidistat, and constant running. These remove water from source. We also have positive pressure systems. These in essence bring in air from the outside via the eaves and push it out, say, onto the landing. The air outside, of course, being drier. We then create a slight positive pressure in the property which pushes out moisture-laden air. The one on the right at the bottom shows us a positive pressure system designed for use in a flat. So the positive pressure unit then sets up a positive pressure internally, bringing in the drier air from the outside via the eaves, and this pushes out the damp air in the building as a whole. Constant running fans, such as ones using in a bathroom and kitchen, these are designed to, for want of another word, suck out the damp air or push out the damp air, and it's replaced with drier air from other parts, including the outside, because a negative pressure is set up and the dry air moves in. Open windows, not too easily if you live in a ground floor flat, say in a city, but it works. No obstruction to air vents. Trickle vents in double glazing. On their own probably do very little, but with other systems such as fans and PPIs, excellent. Given that major areas of water generation are bathrooms and kitchens, it really is important to remove that water at source. Reducing subfloor condensation will first of all reduce internal moisture levels, because such moisture with a higher vapor pressure will pass beneath the floor where it's colder. We should maintain good airflow, and if we have a damp oversight, then we can put polythene over it to slow down evaporation. I mentioned it earlier, but the principle of ventilation is to replace the internal moisture-laden air with drier air from the outside. In other words, we're diluting the internal air with dry air. It's therefore imperative that the air dilution concept is fully understood. There are, however, in relation to landlords and rented properties, there may be implications in relation to the rate of ventilation, mostly with fans and open flues, and a gas safety inspection by GasSafe may be. Improve heating, make it constant, not intermittent. Has other advantages of raising the temperature of surfaces of walls, etc., and lowering the humidity in general, therefore lowering the risk of condensation and mould growth. In reality, ventilation and heat are basically controllable factors and should be the first items assessed, and if possible installed or improved. Provided no obvious excess moisture production, lifestyle overall, namely talking about putting lids on pots and pans and other items, should not be the first point of control. One should therefore keep the relative humidity in a domestic property below an average of around 60% at 20 degrees. This should be the same for any property, irrespective of size and what we could regard as normal occupation. If we cannot achieve this average, then one needs to investigate why. Ventilation, heat, lifestyle, for example, drying clothes over radiators. We saw this earlier, the effects of heating on wall surfaces, especially intermittent heating, but it does show that wall surfaces do heat up very quickly and therefore lower the relative humidity of any air in the boundary layer against that wall. We saw this, how condensation can occur at various times, well beyond the times that we expect it, not during the day, perhaps during the early morning. Reduce sources of moisture. Don't use bottled gas heaters, etc. Don't dry clothes over radiators, unventilated dryers. This activity can overload even the most efficient ventilation and heat systems. Improve surface temperatures, we can insulate. Improve the thermal properties of walls, keep them dry. If one gets water penetration into a wall, not necessarily through it, then that lowers the thermal property. If we can stop that, say by an external silicon coating, then the thermal property of the wall will improve. Dehumidifiers are good. However, for moulds we need to eliminate the moisture causing the problem, and this is followed by. But it should be fully appreciated that the risk of indoor air quality problems leading to these organisms is greater in a distinctly damp internal environment than a dry one. It therefore becomes imperative that nobody should persistently occupy a damp internal environment, and it is essential therefore to get the building back into a suitably dry, clean state. So let's go back again. For the average domestic environment we have mould. But then do you need to require a mould expert when it's found? No. If you can recognise a mouldy orange, you can recognise mould anywhere. You are now a mould expert. So what would you do if you found mould? Would you go and take samples, get them analysed? Indeed, if these were allegedly innocuous, would you leave it? The answer is no. You don't change your corrective procedures based on the species of mould. The cause is the same, water. And this cause is irrespective of the mould type. Control the water, that is the fix. It's impossible to eliminate all mould and mould spores in the indoor environment, and similarly, visible mould, although not a precise measure of exposure, is probably the clearest risk indicator for potential exposure. Air sampling for fungi should not be part of a routine assessment. Decisions can be made about remediation based on a visual inspection. Furthermore, it is only a snapshot, as we'll see in a minute. The primary objective is based on guidelines published between 1993 and 2004, that is, remove visible mould growth and return material surfaces to a satisfactory condition. Finding hidden mould is difficult and expensive. There are, however, odd occasions where one may have to look for it. Searching, therefore, for hidden mould is fear-based marketing, virtually never needed, and expensive. And remember, its visible mould is the reasonable endpoint. Going back then to air sampling, here it shows the inherent variability in air sampling for moulds. Get massive variations in very short time periods, even using the same traps positioned in opposite directions. So there is these massive changes can take place over very short periods of time. Therefore, we are only reading a snapshot of what is going on. There will be a large difference, for example, between sampling while somebody's walking in the room and sampling possibly with all the windows open half an hour later. Sampling for moulds is almost irrelevant. These figures, by the way, are by kind permission of Forensic Applications in Bailey, Colorado. So what do we do? Well, the aim is to keep a reasonably low relative humidity, that is below about 80%. This avoids the development of mould growth. And remediation of the conditions that lead to adverse exposure should be given priority, as identified in the World Health Organization 2009. And very importantly, building owners are responsible for providing a healthy workplace or living environment that is free of excess moisture and mould by ensuring proper building construction and maintenance. The occupants are responsible for managing the use of water, heating, ventilation and appliances in a manner that does not lead to dampness and mould growth. Therefore, it splits the responsibility between the landlord, effectively, and the occupants. Visual and olfactory inspection is the most important step. Cleaning up is complete when there is no visible mould, there are no mouldy odours, and, very important, you have fixed the moisture and water problem so that it will not recur. And again, a repeated theme is most practical approach is simply to eliminate all visible mould growth and smells from the environment. So considering cleanup, if moulds are found in a building, prudent practice recommends that visible mould be removed. It is very unlikely that hidden mould poses a problem. Use the simplest and most expedient method that properly and safely removes mould. There we are. Wash down, anti-mould washes, brushing with HEPA filter, and indeed steam cleaning is reported particularly effective. However, very heavily contaminated material may not be readily cleaned and may have to be removed. Please note that if there is a significant amount of mould present, if it is positively known that occupants have distinct medical conditions which could potentially compromise their health, then speedy clean-up using appropriate control protocols should be put in place. There are issues other than toxicity and allergic responses attributed to mould that are experienced by atopic individuals. And these are frequently the same responses that might arise in a sensitive individual exposed to pollen, dust, house mite feces or animal hair. So it is therefore important that fixing the damp reduces and retards other organisms or items which are implicated in potential problems in persistently damp buildings. But it is extremely important that if it becomes known that a sensitive individual might suffer harm from any such environmental conditions, then professional medical advice should be immediately sought by those individuals. Indeed, if anyone complains of ill health, then they should always seek medical advice from those qualified. And finally, no one without a medical degree should offer opinions on health of patients, and no practicing physician should assume a cause and effect from the limited data available on one patient or even a group. Anti-mould washes, bleach or a suitable biocide, continuing with control of condensation and mould. Anti-mould paints are very useful where the problem is severe, for example in difficult areas such as, and there's an anti-mould paint after 10 years of exposure. On the left is the normal paint, on the right, under the same conditions, is the anti-mould paint. Very effective. For interstitial condensation, most of the above, but especially improved ventilation, plus remove any external vapor-resistant layers. This will allow water vapor to pass freely out through the wall. And install an internal vapor control layer on the warm side. This slows the water vapor into the wall, thus reducing the risk of interstitial condensation.